Hey, what's up, guys? Chung here again. And today I want to talk about this LeetCode problem here. Number 792, number of matching subsequences. So you're given like a string S and a dictionary of words here, and you need to find the number of the words that is a subsequence of S. So what does the subsequence means, right? So for example, this one, the subsequence means you have to maintain the same sequence of the previously source as, but that does not has to be continuous. So for example, this like ACD here, it's A, C, and D. That's a valid subsequence. Same thing for the ACE here. But uh, if it's a C, D, B, then this one is not like a valid subsequence because C and D is fine, but after C and D, there's no B. Okay, so pretty straightforward, right? And but the tricky part of this problem, or the difficulty for this problem, is the length of S is pretty big. As you guys can see, it's 50,000. Okay, and I believe many of you can come up with a like brute force like solution, which is like all the for each word. Okay, we loop through we loop through basically all the we loop through the S here. For each word, we loop through the S, and we'll see. Basically, we're gonna have two pointer. So the first pointer is the S here. Is is the S, and every time the S pointer will keep moving forward, and we have another second pointer for our word here. And for our second pointers, we're only moving forward if the current S character is the same as A. Okay, so for example, it's A, and then we move forward as C here. But now this one is B. B is not the same as C, so we second pointer stays the same, and but the first pointer still moving. Now it's C. Okay, C is the same. We move to D, and then D is the same. We're outside here. Okay, and when this one is finished, and when the second pointer is outside of the words range here, we can stop. We know, okay, we find a match, right? Otherwise, we 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 didn't find a match. Okay, so as you guys can see, that for that, the complexity will be the length of S times the words times is 50. So it's pretty huge number, right? Because the reason being is okay, you know what? Maybe I can just try to implement this one, the first word version real quick, so we can try to like optimize on top of that. Mm, so I'm gonna define the subsequence number here, right? Subsequence helper functions here. So the input will be a word here. So like I said, I'm gonna have like so so the first pointer, I'm going to use a for loop uh, in S, okay? And then I'm going to define the second pointer for the cardinal word here. And like I said, um, basically if I, right, if I is smaller than the length of word, and C is equal to the word dot I, then we do I plus 1. So since I'm going to do a word I here, I need to check the range. Okay, and here basically if I is equal to the length of word, okay, we simply return true here, right? This is like an early termination here. I mean, and in the end we still have to check I equals to length. Okay. Yeah. So basically, this is how we do the check here, right? Basically, we loop through each character here. We only move the second pointer forward as we when we find a match. Okay. And in the end, we simply check. Okay, so if the I currently is the same as the length, that should be pretty straightforward, right? Because at this moment, for example, here, uh, the I will become to 3, right? Which is the length of this word. I'm doing this one as like a early termination here, but this one won't affect the time complexity. Okay, let me finish here. So, and here we're gonna have like answer equal to 0 and simply do a for each word, right? In words, we do a if is subsequence, okay? Word we do answer +1, okay? And we just return the answer. This part is pretty straightforward, and it's this part, okay? Because why this thing doesn't really help us with the performance is because let's say the word is P and Q, okay? And the S, how about the S? Let's say the S is P, P, P. There are like so many P's. And the last one is Q. Let's say there's a 49,999 P's here, okay? But the last one is Q. So in that case, we have to loop through basically the entire S, right? Yeah. And then we can exit the loop. So basically this one will be basically the n times m times k, right? Yeah. So it's going to be n times m times k, which will be a lot. That's going to be a TLE in this case. So do we have a better options, right? So the answer is always yes. And so the way we're doing this, we can have a better solution is like we can maintain the indices like map for each of the character. Let's say uh let's say we have like this A, B, C, D, B, and E. So with this one, we just maintain the key will be the letter and the value is the list of the indices for this letter. So A is 0, B is 1 and 1, 2, 3, 4. B is 1 and 4, right? C is 2 and D is 3, E is 5. Okay. So how can this one help us, right? So as you guys may have already noticed that, so this is a list and the list is sorted since it's indices of this ladder, so it's always sorting. That can make it a perfect candidate as a binary search. Basically, we don't have to loop through from the beginning to the end to find the next available B, next available, I mean, character, if it exists. So basically, the basic idea here is that we're gonna loop through the word here. Let's say we have a word like hmm, let's say we're trying to find like a D, B, and B. Okay, so every time when we see a letter here, and we'll try to see if this letter can be found, right? But in order to do that, we have to keep maintain like a previously put position. So it means that from the previously position, can we find this letter, right? In its indices list. So this is how it works. So at the beginning, this previously position will be -1. I'll explain a little bit more why we need a -1 instead of 0 at the beginning. So let's say for the when we see this is D here, and we find, and then we'll try to look for the indices for the D in this list here. So then we find, okay, it's 3. It's we find 1, and the indices will be 0 in this case, right? We find the 0, we find the 3 here, and now we know, okay, so now the global position is 3 here. So now the previously position will become 3, because we know since we find 3, anything after this D has to be greater than the 3 here. That's the basic idea. And now we're at this B here. Okay, so when we're at B here, we will be looking for the B's indices list in this case, which is 1 and 4. And we're trying to find, okay, basically, is there any indices in this B's in this index list that is greater than 3, right? So how can we do that, right? Basically, we just use a binary search. We use a binary search to see we look for the position where we can insert this 3 here. Inside, we can insert into this list here. And in this case, we can insert into here, basically. And as long as that insert position is not outside of this list, then we know, okay, there is at least another another indices which is greater than the previously position, which means, okay, this one can be matched, right? So okay, so then we find like a position is 1, because we need to find the the minimum position, right? This one can be inserted. So in this case, we find the position is 1, and now we know, okay, so the next matched letter will be B in the index 4 here. Okay, so now the 3 will become 4. Okay, yeah, and now we're moving to the last B here. And when we're looking for the B here, basically we're looking for, okay, so I'm trying to insert 4 uh, into this list here. That's why when we do the insert, we're gonna use the bisect. Uh, this like this the Python's built-in library. We're gonna use the bisect right. Okay. So in this case, because that's why the reason we're doing the right instead of left is we want to distinguish 4 and 3 here, because for 3 it's giving us like a position 1 here, but if we're doing a bisect of left here, when we try to insert 4 here, it will also give us a 1 here instead of 2, right? Which will make us which would make it makes it impossible to tell the difference. That's why we'll be using a bisect right here. And okay, I think that's pretty much the idea here. And let me try to code these things up. Okay, so I think I can keep most of the structure here. Yeah, this part is fine. Yeah, I just need to maintain like indices map here. So since it's a list, I'm going to initiate this one as to default a list, and I simply do a character in enumerate as here, right? And then the indices map. So for this character, what's the indices? I keep appending to this list. Yeah, it's pretty straightforward, right? That's how we create this indices map here. And yeah, and other than that, it's just to previously kind of position, right? -1. So for character in the word, right? And uh, we need to first check if basically if the C is not in the indices map, then we can simply return false because it's pretty obvious, right? If C is not even in the S, so obviously this word is not a subsequence. Okay. After that, then we know we need to find, right? We need to find. Okay, can we find like the next appearance for this character that appears after this previously position, right? So, and the source is this indices map for this character. Okay, that's why I'm going to use the bisect right here to do. So the source is the index map dot c, right? So that's our source, and the value we're looking for is previously position. See, that's why I'm using the -1 instead of 0, because let's say there's like a 0 and a 4, okay, and there are like two b's here, right? And so for the first time, right, we find if we're trying to find 0, and since we're doing like a bisect right, it will give us uh one indices will give us 1 instead of 0, right? So but in this case, what we really want is 0 because the first one is always 0 indices. That's why I use -1 to make sure for the first time I always get 0. Okay, cool. So, and after that, I simply check if the indices is the length of the index map dot c, right? Basically, this is what I told you guys. And if this indices it's somewhere here, basically, if we cannot find any indices is greater than the previously position, right? In this case, it's going to be the length of that because it's outside of our indices list. Then we know there's a this current this letter C is not a match, so we have to return false. Okay, and if we can find one, right, and then we just need to update the previously position with the with that indices, which will be the map dot c dot index, right? Because this indices is the first one. Basically, it's the first one that we can find, which is uh, the first one we can find, which is greater than the previously position, right? And yeah, and then we just use that one to update to be our previously position, so that the next time when we have a letter, this is going to be our base case. Yeah. And if everything works fine, we simply return true here. Okay. Mm, yeah. Yeah, I think that's pretty much it is. Let me try to run this code. Oops. Oh, sorry. If. Yeah, we're missing a if here. Yeah, this one passed. Accepted. Let's submit it. Yeah, success. Okay, successful. Yeah, and yeah, it's so pretty tricky, huh? Yeah, I think the binary search is always kind of tricky one, and especially if you need to combine it, you need to convert this problem into a binary search problem, which makes it even trickier. And yeah, so let's take a look at this time complexity now. So to maintain like a indices map, it's gonna be the O, and let's say this N, M, and K. Okay, so the first one is O of N, right? And now this, so for yeah, for each of the word, right? So for each of the word, that's a M, right? So the first one is M times for each letter. For each letter, that's the K, right? Times binary search. So the worst case scenario, let's see this all there's it's they're all the same. They're all the same letters, which means the list the length of the list is the same as n. So it's going to be a log n, right? As you guys can see, so we have improved this this uh time complexity for scanning this ads from linear, which is O(n), to a log n, which is a huge improvement. Yeah, because this n is our bottleneck, and to improve it to a log n is a huge improvement. So yeah, and the space complexity is, yeah, of course it's O(n), right? Yeah, because we are maintaining indices for each of the letter here. Yeah, I think that's, yeah, for a recap, what can I say about this problem? I mean, uh, I guess you just have to know there is this like indices way where you can speed up the search of this subsequences problem. I guess it's you just have to remember whenever you need to find a subsequence from a source like string here, instead of instead of searching the strings one by one, there is a better way. Basically, you maintain like each letter's indices list, and then you do a binary search. Basically, the idea here is that we maintain like previously positions, and we try to find if there is a like hmm, if for with this letter with the current letters like indices list, can we find uh, another appearance of this letter that appears after this previously position, right? And if we can find it for all of the characters, then we know, okay, so this word must be a subsequence of the source string here. And to do that, you have to implement this like binary search. I think for this one, maybe you can try to implement by yourself, or but here I just took a shortcut by using like the Python's built-in binary search function to help me simplify my code a little bit. Hmm, yeah. Okay, cool, guys. I think that's it for this problem, and thank you so much for watching the video. And let me know if you guys have any comments or anything or any suggestion. And stay tuned. I'll be seeing you guys soon. Bye bye.